Okay, picture this. May 8th, 1981, Winter Park, Florida. A sycamore tree just disappears.
Vanishes. No storm, nothing, just gone.
And that was only the beginning. Over the next few days, this hole just kept growing.
Yeah, swallowing a house, other buildings, the town swimming pool.
A road, and get this, a bunch of brand new Porsches from a dealership nearby.
It sounds like something out of a movie, really. But it's a perfect, if dramatic, illustration of what's happening underground.
Right, the culprit wasn't some monster, it was groundwater.
Exactly. Over, well, a very long time, groundwater had been dissolving the limestone bedrock underneath, creating hidden caverns.
And eventually the roof of one just couldn't hold up anymore.
That's it. Collapse.
Yeah.
And that's how Lake Rose formed, right there.
Wow. It really makes you stop and think about what's beneath us. We just walk around on it every day.
We do. And that event, as strange as it was, highlights a huge fact. Most of the Earth's liquid freshwater isn't in rivers and lakes.
No, it's underground. And the number is staggering, 123 times the volume of all the lakes, rivers, swamps combined.
That's the figure. It's this vast hidden reservoir, absolutely vital for agriculture, industry, our homes, everything, really. About 2/3 of the fresh water we use globally comes from groundwater.
So this isn't just some weird Florida story. It's a window into this massive, critical system.
Precisely. So for this deep dive, we really want to get to grips with groundwater.
Okay, like where does it come from? How does it get down there?
Exactly. Where does it reside? How does it move? Because it does move, just very slowly usually.
And how does it get back out? Springs, wells, that sort of thing.
Right. And we'll also look at how we humans impact it and some of the amazing landscapes it creates, like hot springs and caves.
Cool. Okay, so let's start with the basics. Where does groundwater actually live, so to speak?
Well, it ties back to the hydrologic cycle, which you might remember.
Yeah.
Rain falls, some runs off, some evaporates.
And some soaks into the ground.
Infiltration, right?
Infiltration. The ground isn't solid. It's full of tiny, interconnected open spaces. Think of it like a giant, complex sponge.
A sponge made of rock and soil. Sort of, yeah. Geologists call any open space a pore. And porosity is the term for the total amount of that open space in a rock or sediment sample, usually given as a percentage.
Okay, porosity. And there are different kinds, primary and secondary.
Right. Primary porosity is the space that's there when the rock or sediment first forms, like the gaps between sand grains if they don't pack perfectly together.
Makes sense. Like pouring marbles in a jar, there are always gaps.
Exactly. And how well sorted the grains are matters. If you have lots of different sizes mixed up poorly sorted, the little ones can fill the gaps between the big ones.
So poorly sorted actually means less porosity.
Generally, yes, compared to well-sorted sediment where the grains are all roughly the same size. Also, compaction, burying the sediment deep, squishes grains together. And cementation.
That's like minerals gluing the grains together.
Precisely. Both reduce primary porosity in sedimentary rocks like sandstone. But you can get primary porosity in other ways, too. Well, in chemical rocks, sometimes the crystals don't grow perfectly flush against each other. In crystalline rocks like granite, the grains might not interlock perfectly.
Okay. And volcanic rocks. Some look really bubbly.
Ah, yes. Vesicles. Those are trapped gas bubbles from when the lava cooled. That's another type of primary porosity.
So the amount can vary hugely then, like almost none in dense granite, but maybe 30% in loose sand.
That's the range, yeah. Now, secondary porosity is different. It forms after the rock is already there.
How does it happen? Cracks.
Cracks, or fractures, are a big one. When rock breaks, the sides rarely match up perfectly, leaving gaps. And also dissolution.
Groundwater dissolving the rock itself.
Or just the cement holding it together. This creates new cavities or widens existing pores and fractures. We see this clearly in some limestones.
Okay, so rocks have pores, primary or secondary, that's where the water is. But just having space isn't enough for water to move easily, is it?
Excellent point. That brings us to permeability. Porosity is about storage, permeability is about flow.
How easily the water can actually travel through the rock.
Exactly. Are those pores connected? Think of that jar of gravel again. It has pores, porosity, and if you pour water in, it flows through because the pores are connected. Permeability.
So high permeability means easy flow, low means slow flow, and impermeable means basically no flow.
You've got it.
What controls permeability then? It sounds like it's about the connections.
It is. Three main things. How many connected pathways or conduits are there? How big are those conduits? Wider is better. And how straight are they?
Straightness matters.
Yep. A winding, tortuous path offers more resistance than a straight one, even over the same distance. Think city traffic-wide straight highways versus narrow, winding alleys.
Good analogy. So porosity and permeability aren't the same. You can have high porosity but low permeability.
Definitely. The classic examples are cork and vesicular basalt, that bubbly volcanic rock.
Both have lots of holes, right? High porosity.
Lose a space. But in cork, the spaces are sealed off by cell walls. In vesicular basalt, the bubbles are generally isolated within solid rock. Water can't flow through easily. High porosity, low permeability.
Got it. Okay, this porosity-permeability distinction leads to aquifers and aquitards.
Key terms in hydrogeology. An aquifer is rock or sediment that has both high porosity and high permeability. It can store water, A and D, let it flow readily.
That's where we get water from wells.
Right. An aquitard, on the other hand, has low permeability. It might hold some water if it has porosity, but water moves through it extremely slowly. Sometimes you hear aquiclude for something essentially impermeable.
So good aquifers would be like loose gravel or maybe sandstone that isn't too cemented or limestone with lots of dissolved fractures.
Perfect examples. And aquitards, things like shale made of tiny packed clay particles or salt beds, or really tightly cemented sandstone.
And these often occur in layers, right? Aquifer, then aquitard, then another aquifer.
Very common. Which leads to another important distinction: unconfined versus confined aquifers.
Unconfined is open to the surface, like the top is just the water table.
Exactly. Rain can soak right down into it. A confined aquifer is sandwiched between aquitards.
Trapped, like under pressure.
Often, yes, especially if the recharge area where water gets in is higher up, the aquitard's isolated.
Our notes have some really cool specific examples, like the Mahomet Aquifer in Illinois. Glacial meltwater filled old valleys with gravel.
Yeah, during the Ice Age. Then later, glaciers buried that gravel under less permeable stuff, creating a confined aquifer in places. A direct link between past geology and present water resources.
Then there's the Phoenix Basin in Arizona. That formed differently, from crust stretching and basins filling with eroded sediment.
Right, basin and range tectonics.
Right.
Rifting created deep basins, mountains eroded, filling the basins with permeable gravels and sands.
And the Dakota sandstone, that one's huge across multiple states. Old river sediments under shale.
Deposited in an ancient inland sea during the Cretaceous. The sandstone became the aquifer, the shale above it the aquitard. Then the Rockies pushed up, warping it all into a big syncline, a trough shape.
So water gets in way out west where it's exposed, then flows east, confined under the shale. Amazing.
It really shows how large-scale structure controls groundwater flow over vast areas. Then there's the Ogallala, or High Plains Aquifer.
Another massive one under the central U.S., formed from erosion off the Rockies, too.
Mostly, yeah. Rivers dumped huge amounts of sand and gravel, the Ogallala Formation near the surface. It's mostly unconfined, meaning rain can recharge it directly. And it actually sits on top of the Dakota in some areas.
And Florida's aquifers, those are mostly limestone, with big dissolved fractures.
Exactly, formed from ancient marine deposits. That dissolution widening fractures is key to their permeability, and also why Florida gets so many sinkholes like the one we started with.
So aquifers vary a lot depending on the geology. Okay,
Yeah.
let's talk about the water table itself. That's the top of the saturated zone.
Correct. Below the water table, in the saturated zone, or phreatic zone, all the pore spaces are full of water. That's technically what we mean by groundwater,
And above it is the unsaturated zone, where pores have air and some water.
also called the vedose zone. The very top part has soil moisture held by capillary action.
And just above the water table, there's that capillary fringe, water wicked up slightly.
Yeah, due to surface tension, it's usually pretty thin, maybe a few inches to a foot or so.
How deep is the water table usually? Must vary wildly.
Hugely. It can be right at the surface in swamps or next to rivers. In humid areas, maybe a few meters down, tens of meters. In deserts, it could be hundreds of meters deep.
And it goes up and down with rainfall.
Absolutely. Drops in dry seasons, rises in wet seasons. That's why some ponds or streams are seasonal. They dried up if the water table falls below their bed.
How deep does groundwater actually go in the crust?
Surprisingly deep sometimes. It can circulate in basement rock along fractures, maybe down 15 kilometers or more.
Wow! What stops it?
Eventually, heat and pressure get too high. Water becomes a hydrothermal fluid involved in metamorphism, and the rock itself starts to flow plastically, closing fractures. So usable groundwater is mostly in the upper crust.
Okay.
Huh.
And the shape of the water table, is it flat?
Not usually, especially in hilly areas. It tends to mimic the land surface above it, but in a more subdued way. Higher under hills, lower under valleys.
Because the water moves too slowly to just flatten out immediately.
Exactly. The relief, the ups and downs of the water table is less extreme than the land surface.
And what about perched water tables? That sounds interesting.
It is. Imagine a lens of impermeable stuff, like clay, within a larger sandy aquifer. Water soaking down hits that clay lens and gets trapped above it.
Creating a little zone of saturation above the main regional water table.
That's a perched water table. It can feed shallow wells or springs locally.
Fascinating. All right, so we know where it is, what the water table is like. How does groundwater actually move? It's not just sitting there.
Definitely not. It's always moving, just usually slowly, driven by gravity and pressure differences.
In the unsaturated zone, it just percolates down due to gravity, right?
Pretty much. But in the saturated zone, below the water table, it's more complex. Gravity pulls it down, but pressure can push it sideways or even upwards.
Where does the pressure come from? Just the weight of the water above?
In an unconfined aquifer, yes. The deeper you go below the water table, the more water is pressing down, so the higher the pressure. The weight of the rock itself is supported by the rock grains, not the water.
So depth equals pressure. But what if the water table is sloped?
Then pressure can vary even at the same elevation, depending if you're under a high point or low point of the water table.
Okay. Now, hydraulic head. That sounds important for flow.
Crucial. Hydraulic head is the total potential energy driving flow. It combines the elevation of the water and the pressure at that point.
How do you measure it?
Drill a well to that point and see how high the water rises in the pipe. Higher water level means higher hydraulic head.
And water flows from high head to low head.
Always. That's the fundamental rule. In simple terms, for unconfined aquifers, it usually means flowing from where the water table is higher to where it's lower.
But not in straight lines, you said. They follow curves.
Generally, yes, concave up curves, resulting from the interplay of gravity and pressure. Flow paths go from recharge areas
Where water soaks in, heading downwards.
to discharge areas where groundwater flows back up to the surface, like in streams or springs.
And you can have local flow paths, just short trips, and regional ones that go really deep and far.
Exactly. Local flow might take hours or weeks, traveling maybe a few kilometers. Regional flow across a basin could take centuries, even millennia, traveling hundreds of kilometers.
Wow, millennia underground. That's old water and the speed. Much slower than rivers.
Oh, vastly slower. Typically centimeters, maybe a meter a day. Rivers flow kilometers per hour.
Why so slow?
Several reasons. The paths through pores are tortuous, much longer than straight lines. Surface tension holds water to grain surfaces, and there's friction against the pore walls.
Like running an obstacle course blindfolded.
Something like that. And the speed depends on two main things: the slope of the water table, or more accurately, the hydraulic gradient.
The steepness of the energy drop.
Right, and the permeability of the material. Higher permeability, steeper gradient means faster flow.
Which makes sense. Easier path, stronger push. Darcy's law describes this mathematically.
It does. It relates flow rate, discharge, to hydraulic conductivity, permeability, and a hydraulic gradient. Q equals Ka times the head difference over distance.
Okay, so gravity and pressure drive this slow movement. How do we actually get this water? Obviously, springs are one way.
Springs are the natural outlets, where the water table meets the surface, or where geology forces water up. Humans have used them forever. Oldest wells found are maybe 9,500 years old.
Wow. And springs can form in lots of ways. Valley floors, hitting impermeable layers, perch tables.
Fractures channeling water, even artesian springs from confined aquifers under pressure. Desert oases are classic examples of life depending on springs.
Vital spots. But mostly now we use wells.
Right. An ordinary well just needs to penetrate the aquifer below the water table. Water seeps in to match the water table level.
Unless you drill above the water table or into an aquitard, then it's a dry well.
Or it might be seasonal if the water table drops too low.
And finding a good spot, dousing doesn't actually work, right?
No reliable scientific basis for it. It's more about understanding the local geology or just luck.
So once you have a well, you pump the water out. But if you pump too fast,
You create a cone of depression. The water table around the well lowers because you're taking water out faster than the aquifer can replace it right there.
and that can make nearby shallow wells go dry.
It certainly can. It pulls the water table down below their reach.
Okay, what about artesian wells? Those sound different.
They tap into confined aquifers where water is under pressure from the overlying aquitard.
So the water rises in the well by itself?
Yes, it rises above the top of the aquifer level. If it rises but stays below ground, it's a non-flowing artesian well. You still need to pump it the rest of the way.
But if it comes all the way up and flows out?
That's a flowing artesian well. Same principle as an artesian spring. just through a drilled hole instead of a natural fracture.
The analogy in the notes is like a city water tower creating pressure.
Exactly. The elevated recharge area of the confined aquifer acts like the water tower. The level the water would rise to in wells is called the potentiometric surface. If that surface is above the ground level where the well is, water will flow out.
Can happen locally in valleys or regionally across big plains if the aquifer is tilted right?
Precisely. It's all about that pressure from the higher elevation recharge zone.
Okay, let's switch gears to something hotter. Hot springs and geysers. Groundwater meeting Earth's heat.
Fascinating stuff. Hot springs are just springs where the water is, well, hot. Significantly warmer than the local groundwater average, usually 30 to over 100 degrees Celsius.
How does it get so hot?
Two main ways. Either groundwater circulates really deep, kilometers down, and gets heated by the normal geothermal gradient Earth getting hotter with depth, then finds a path back up. Or it's in a geothermal region near recent volcanic activity. Magma near the surface heats the groundwater much more quickly and shallowly.
Like Yellowstone or Iceland?
Prime examples. And because hot water dissolves minerals better, hot spring water is often very mineral-rich. People use them for mineral baths.
And they create cool features like colorful pools from microbes.
Yep, thermophilic bacteria and archaea loving the heat and sulfur. Also, mud pots, hot water mixing with volcanic ash or clay, and travertine terraces.
Where the cooling water drops its dissolved minerals.
Exactly. Calcium carbonate precipitates out, building those beautiful stepped formations.
Living near these sounds potentially hazardous, but also useful for energy.
Both are true. Geothermal power and heating are big benefits, but steam vents and eruptions are risks.
Okay, now geysers. The really dramatic ones, like Old Faithful. How do they work? They erupt periodically.
It's all about the underground plumbing, a network of fractures in hot rock filled with groundwater that gets heated.
But water boils at 100 C, right?
At sea level pressure, yes. But pressure increases with depth. So down in the geyser's plumbing, water can be heated way above 100 C, but stay liquid because of the pressure. It's superheated.
A natural pressure cooker.
Pretty much. Now, as some of this superheated water starts to rise, the pressure drops. Eventually, some of it flashes into steam.
That pushes water out the top.
Right. And that sudden expulsion drastically lowers the pressure on the superheated water, still deeper down.
Triggering a chain reaction? More boiling, more steam.
Exactly. A rapid, violent boiling converts much of the remaining water to steam, ejecting everything forcefully upwards in the eruption.
Then it calms down, refills, reheats, and the cycle repeats.
That's the mechanism, the delicate balance of heat, water, pressure, and plumbing.
Amazing physics. Okay, let's turn to the less amazing side groundwater problems caused by us. It's such a critical resource.
Absolutely critical. Drinking water, irrigation, industry. We rely heavily on it, especially as surface water gets scarcer. Something like 80–95% of withdrawn groundwater goes to agriculture and industry.
But it's not infinite. We're using it faster than it refills in many places.
That's the core problem. Groundwater depletion. On human timescales, it's often non-renewable. Population growth, irrigation for the green revolution, industry. Demand has exploded.
And withdrawal rates exceed recharge rates significantly in some major aquifers, like 20% globally being depleted.
Some estimates are even higher in specific regions, especially arid areas like the U.S. Southwest, where recharge is naturally slow. Climate change might make it worse.
The main consequence is the water table dropping.
Yes. Wells go dry, springs stop flowing, rivers shrink or disappear if they rely on groundwater input. We have to drill deeper, which costs more.
The gray satellites actually measure this loss of water mass from space.
They do, by tracking tiny changes in gravity. They've shown huge depletion in places like California during droughts and farming areas in India. Even diverting surface water, like in the Everglades, impacts groundwater levels.
Beyond just running out, what other problems does overuse cause? Saline intrusion.
A big one in coastal areas. Freshwater normally floats like a lens on top of denser saltwater that seeps in from the ocean.
But if you pump out too much fresh water near the coast,
You draw the saltwater interface upwards, it can get pulled into the well, contaminating the freshwater supply, called saltwater intrusion or upcoating. Very hard to reverse.
and land subsidence, the ground actually sinking.
Yes. The water pressure in the pores helps support the weight of overlying sediments. Remove the water, and the pores can collapse, especially in clays and silts,
The aquifer compacts, and the land surface above it sinks.
permanently reducing the aquifer's storage capacity, too. It can cause fissures, tilt buildings, damage infrastructure. San Joaquin Valley in California has sunk up to 9 meters in places, Venice's flooding is partly due to subsidence from past pumping.
Scary stuff. Can we do anything to help recharge aquifers?
We can try. Directing surface water into infiltration ponds or actively pumping treated water back underground artificial recharge. Protecting natural recharge areas is key.
Okay, what about contamination? That seems even harder to fix than depletion.
Often it is. Contaminants can make water unusable for a very long time. Sources are numerous. Agricultural chemicals, industrial waste, leaky landfills, septic tanks, gas station leaks, radioactive materials, acid mine drainage.
The list goes on. And these contaminants form a plume that moves with the groundwater flow.
Exactly. Dissolved contaminants travel with the water, and they can travel surprisingly far, tens of kilometers potentially, polluting wells and streams downstream. Pumping wells can even change the plume's direction.
So prevention is crucial, like putting potential pollution sources on impermeable ground, using liners.
Yes, careful siting and containment are key. Secure storage for hazardous waste is vital too.
But if contamination happens, can we clean it up? Remediation?
It's very challenging and expensive. Nature does some cleanup absorption by clays, natural breakdown by microbes, but usually we need active methods.
Like pumping out the bad water and treating it.
Pump and treat, yes. Or injecting clean water or steam to push the plume towards extraction wells. Bioremediation involves stimulating microbes to eat the contaminants.
Permeable reactive barriers,
Right.
like underground filters.
Walls of material like iron filings that chemically react with and neutralize contaminants as groundwater flows through. But cleanup is often slow, costly, and incomplete.
A cautionary tale. Now, we usually worry about too little water, but can too much groundwater or rising water table also cause problems?
It can. Obvious one is flooded basements. But geologically, a higher water table increases pore pressure in slopes.
Which can reduce the strength of the soil or rock.
Exactly. Potentially weakening slopes and triggering landslides or slumps. So like many things in nature, it's about balance.
Okay, let's end on a more wondrous note. Caves and karst landscapes. Groundwater as a sculptor.
A truly spectacular side of groundwater's work. Caves, natural underground openings large enough to enter out of direct sunlight, often formed by dissolution.
Mostly limestone dissolving in slightly acidic groundwater.
That's the most common way. Rain picks up CO2 from the air and soil, forming weak carbonic acid. That acid slowly eats away at calcite, the main mineral in limestone.
Though some caves, like Carlsbad Caverns, form from sulfuric acid, linked to oil and gas deposits.
A smaller percentage, yes. Yeah. Microbes convert sulfur compounds to hydrogen sulfide gas, which then oxidizes to sulfuric acid, a much stronger acid.
Where do caves actually form? Below the water table.
The current thinking is most cave development, or speleogenesis, happens right at or just below the water table. That's where the water is often most chemically aggressive and flow is fastest. Fluctuating water tables can create multiple levels.
And caves aren't just tunnels. They have big rooms, passages, underground rivers.
Their shape reflects the rock structure. Passages often follow joints or fractures, secondary porosity providing pathways. More soluble layers might form larger chambers.
What conditions favor big cave systems? Thick limestone, enough rain, active groundwater flow.
Right, temperate or tropical climates usually.
Yeah.
And organic rich soil above helps make the water acidic.
Then, when the water table drops and the cave fills with air, we get speleothems, pave decorations.
Exactly. Water still dripping from the ceiling is saturated with dissolved calcite. As it enters the air-sealed cave, CO2 escapes, water evaporates slightly, and calcite precipitates out.
Building up dripstone formations over ages, like stalactites hanging down.
And stalagmites growing up from the floor where the drips land.
If they meet, they form a column.
Right. You also get flowstone, like frozen waterfalls on the walls, and delicate soda straws, draperies, often translucent and beautiful when lit.
Now, when these caves near the surface start collapsing and the surface itself dissolves, we get karst landscapes, named after a region in Slovenia.
The Crust Plateau, yes. Karst topography is the distinctive landscape formed by dissolution of soluble rock like limestone, both underground in caves and at the surface.
With features like disappearing streams sinking into the ground.
And sinkholes, those circular depressions from surface dissolution or cave roof collapse. They can be huge.
Natural bridges left behind from old cave roofs. Tower karst in the tropics.
Like those amazing steep limestone peaks in China or Vietnam. It's a whole landscape, sculpted by dissolving rock over long time scales. First caves form, then the water table drops, speleothems grow, and eventually the roof collapses, creating sinkholes, ridges, and towers.
A fascinating process. And caves aren't empty, right? They have life.
Definitely not sterile. Bats, insects, spiders use them. Unique fish and crustaceans live in cave streams, often blind and without pigment.
Adapted to total darkness, and even weird microbes like those snottites.
Yes, sulfur metabolizing bacteria in some Mexican caves. Life finds a way even in these extreme environments, supported by the groundwater.
Well, this has been a truly comprehensive journey into the world of groundwater. From sinkholes to aquifers, contamination to caves, it's clear how vital and impactful this hidden resource is.
It really is. Shaping landscapes, supporting ecosystems, providing essential water, but also vulnerable to our actions.
It really underscores the need for careful management. Thinking about increasing water demand and the problems of depletion and contamination, what innovations or policies do we need for sustainable groundwater use in the future? Especially knowing how interconnected everything is in the water cycle.
That's the crucial question for all of us, isn't it? It might be worth you, the listener, looking into where your own local water comes from and what the groundwater situation is in your area.
Definitely food for thought. And if you want to dig deeper, our source material has great visual features on Florida sinkholes and Puerto Rican karst, plus GeoTours topics on desert irrigation, the Everglades, Yellowstone, and global karst distribution. Lots to explore.
Absolutely.
So I think we've successfully covered the breadth of this chapter, the core concepts, processes, examples like the aquifers and geothermal areas, the diagrams we mentally walked through, and the real-world applications and problems. It's been a thorough deep dive.